you can you say that we can do the following. We can say, okay, we have to bound this guy, which is here, by something first, which is independent of n. Okay, and you say, okay, you say I can write expectation of xn, indicator function of xn bigger than a. You say that since xn is less than x, what I can do is to bound it by expectation of x. Okay, x is positive, in fact. Okay, but what do you do of this guy, this indicator function?
Well, I believe we can replace this indicator function by the whole. Just
but if you replace
not the whole, not the whole, but oh, let me think.
Because
well,
if you replace, okay, I agree that this indicator function is bounded by 1, but if you replace it directly by 1, it will not go to 0.
I see. I believe we can replace it with indicator function xn, x instead of xn, isn't it?
Okay, yes, you're right. And why is it true?
Because xn, we will not just make it smaller, because xn is great, x is greater than xn, then the indicator function will cover just more, I believe. Yeah, just
yes, more. Okay, yes, it is correct. So I just give the formal argument to say it. So you know that indicator function. What is indicator function? Indicator function of a set C is 1 if omega is in C and 0 if omega is not in C. So the fact that xn is less than x. So if xn is bigger than a, this implies that x is bigger than a. This comes from this inequality. Okay? If some omega is such that xn of omega in absolute value is bigger than a, it implies that x of omega is bigger than a. And you know that if some set B is included in some set C, then 1 over B is less than 1 over C. So one indicator function of xn bigger than a is less than indicator function of x bigger than a. So it is what you expressed previously, but if is what you said is because of this property. If you have an event which is included in some other event, the indicator function of the event B is less or equal to the indicator function of the event C. And so since this event, when I write this implication, it means that the omega for which xn of omega in absolute value is bigger than a is included in the set of the omega for which x of omega is bigger or equal to a. So it's the reason for which you have this inequality here. And so it is what you said previously, that in fact this guy, I can bound it in this in the following way. I can say you can say that the expectation of x indicator x is positive is less than the expectation of x indicator function of x bigger than, okay, I can put the absolute value, but it's not useful because x is positive. And so since it is true for any n, we have the super n of the expectation of xn, indicator function of xn bigger than a is less or equal to expectation of x, indicator function of x bigger than a. And then
Well, and then it just we say that x is in L1, so we know that the expectation of tails tends to 0.
Yes, what you use is dominated convergence theorem. You agree?
Yep.
Yes. Okay. So that is going to 0 as a goes to infinity. Exactly by the dominated convergence theorem. Dominated convergence theorem. And so this is a bound, upper bound, which is independent of n. So I have also that the limit as a goes to infinity of the supremum in n of the expectation of xn, indicator function of xn bigger than a, is equal to 0. Okay, it's finished. Okay, good. Perfect. Some questions or no? Okay, so the question number 2 is the following. Assume there exists p strictly bigger than 1, strictly, not greater or equal to 1, strictly bigger than 1, such that the supremum over n of the expectation of x and power p is finite. So there is some uniform bound on the LP moments of the random variable xn. Show that the sequence xn, the stochastic process xn, is uniformly interval. So if you remember, we have to show that we have to bound, in some sense, this expectation of xn, indicator function of xn bigger than a. We have to bound it by something which is independent of n, which goes to 0 as a goes to infinity. So do you have some ideas of how to attack, how to bound it, how to bound this guy? Of course, you have to use this property. Just some idea of what kind of thing you propose to use. You can propose in the chat also. No idea?
Well, the simplest thing is like we can have a limit when p goes to 1 from the top.
But you cannot send p to 1. P is fixed.
Ah, okay, sorry.
It is there exists p.
Yeah, sorry.
You have to bound some product of, you see, it is a product of this random variable with this random variable. What kind of inequality do you know to bound some the expectation of a product of random variables?
Cauchy-Bunyakovsky.
I don't know what it is.
Oh, Cauchy, Schwarz, it's
Cauchy-Schwarz, yes. And the other ones that you mentioned is what?
it's just okay. Third name, just okay. Cauchy Schwarz, yeah. Okay.
Okay, Cauchy-Schwarz, but Cauchy-Schwarz is okay. If I wanted to use Cauchy-Schwarz, what Cauchy-Schwarz will tell me will be that it is the square root, or maybe I can write it. It will tell me that I have the product of Phi's random variable with Phi's random variable. So I could say by Cauchy-Schwarz to be let an expectation of xn square 1/2 expectation of indicator function xn bigger than a, okay, square, but it doesn't change nothing because it is just 1 or 0, 1/2. So this is Cauchy-Schwarz. But what are the information that I have on this guy? I don't have some information about the second moment of xn. You learn in probability theory something which is generalized Cauchy-Schwarz inequality.
Maybe Hölder inequality can be applied.
Yes, exactly. Hölder's inequality, correct. So if I use Hölder's inequality, of course, I have some control of the pith moment of xn. So it makes sense to try to use Hölder's inequality where you make appear this pith moment of xn. So I use, instead of Cauchy-Schwarz, I will use Hölder inequality. So what I will get is that it will be not this exponent, but I will get p 1 over p and q 1 over q, where q, I recall you, is just that 1 over q plus 1 over p equal to 1. Observe that I assume that p is strictly bigger than 1, which is very important. This is what I claim is false if p is not strictly bigger than 1. P strictly bigger than 1 means something over q. P equal to 1, if p was equal to 1 here, it will mean that q will be infinite. But here, since p is strictly bigger than 1, it would imply that q is strictly bigger than 1. No, maybe it is not. Okay, what is important is that q is not infinite. Okay. So, I have this Hölder's inequality. Hölder's inequality. Which is a fundamental inequalities in probability theory. You have the Markov inequality, Bianevich-Chebyshev's inequality, Hölder's inequality, Jensen inequality, and the Cauchy-Schwarz inequality, which is a special case of Hölder's inequality. All these inequalities are fundamental in order to, when you need to bound some expectation of random variables. Okay, so now, okay, what is good is that you see if this guy here is uniformly bounded in N because of his assumption. We know that the supreme over N of his expectation is finite. So let me give some name to this guy. So we call it C, okay, which is a constant, finite constant with independent of N. So I get that this guy is less or equal to C power 1 over P times the expectation. And now it is indicator function of xn bigger than A power Q. But this, it is indicator function. It doesn't change if I take the power Q or not. 1 power Q is a 1, 0 power Q is 0. So it is the same as this one. Okay, so now it remains to bound this guy by something which is independent of M. So what do you propose to bound this guy?
By one.
Okay, but
With just one, maybe.
Yeah, but if you do it by one, okay, I agree that it's correct. But then you need to show that at the end, this guy will go to 0 as a goes to infinity. So if you bound it just by one, it will not go, one is not going to 0. So we have to bound by something depending on a. Because uniform interability, you remember the definition, maybe I have to come back, but okay, so
We can restrict by probability of A.
but what way do you mean by restricting to probability of A?
I mean, the expectation of indicator is a probability, so we should we could use such trick. No.
I don't understand what you mean by restricting. Here you have some indicator function of xn bigger than a. So you want to say that this set xn bigger than a can be restricted to something, or?
Why not? Is just a probability of xn not less than a.
Okay, that I agree that it is correct. Okay, I can write it in this way. Oops. Write it. Okay, it disappeared. Okay, no problem. Expectation of one xn bigger than a. So I agree that this expectation I can write it as I can write it like see 1 over p probability that xn bigger than a. Okay, power 1 over q. And then what I do, because at the end I need some bound which is independent of n, depending on a, I'm going to 0 as a goes to infinity. What do you know as inequalities in order to bound some probability of some event in this form? You have again to use assumption that the LP norms are uniformly bounded.
Now maybe we apply in Chebyshev inequality.
Yes, exactly.
Or something like this.
Yes, exactly. So it will be some, okay, I don't know exactly. Sometimes I'm confused about what the people call Markov's inequality, Chebyshev's inequality, and so on. So just this inequality.
Where the variance in the numerator.
Okay, but then the variance is not a good idea because the variance, we don't have any control of the variance of xn. If you look at the assumption, with assumption, we don't have any.
Agree.
But you can use something which is of this kind of Chebyshev's inequality. It is not the variance, but the LP norm. So I can bound this.
Yeah, I agree. With
okay, it is like the Cauchy-Schwarz inequality is a special case of the Hölder's inequality. Cauchy-Schwarz is just when you take p equal to 2. Here also you can bound it by the expectation of xn power p divided by a power p. Okay, everything power 1 over q. Okay, it is a generalization of what you said, mainly. Here it is this inequality that I wrote, which is, okay, I call it Markov's inequality. It is valid for ADP, P, positive P. Okay, and then now it's good because I have some control of this expectation of xn power P. I know it is uniformly bounded. It is a constant C that I introduced before. So I can bound this guy by C1 over P, and this guy C divided by A, P, everything power 1 over Q, which is, if I simplify, this C1 over P plus 1 over Q divided by A, P over Q. Okay, 1 over P plus 1 over Q is equal to 1. So in fact, it is, okay, it's not very important, but this C divided by A or P over Q. And here you see I have a bound which is independent of N. And this is the first thing that I need. For uniform interpretability, it means that you need some bound which is independent of N, because it has to be uniform. And the second thing is that because I have this A, which is here, okay, P over Q is some positive constant. I know that A, P over Q is going to plus infinity as A goes to plus infinity. So C divided by A power P over Q is going to 0 as A goes to infinity. So in this way, I obtain some control, which is uniform and which goes to 0. So the previous proposition, which was just to replace this indicator function here by 1, was not good. Because then if it is 1, then I cannot say that it goes to 0. It is bounded, okay, I agree. But I need something which goes to 0 as A goes to infinity. It is in the definition of uniform interpretability. So these two examples are quite important, because when you want to show that some sequence of random variables are uniformly interpretable, so usually what we show is that there exists P strictly bigger than 1, so that the expectation of the xn per P is uniformly bounded in N. And then we know that it is uniformly interpretable, so we can apply this kind of theorem of this Dup's convergence theory. Okay, everything clear, or there are some questions? No? Okay, so I imagine that everything is clear. Okay, so now let me come back to the exercises. Okay, so here. So here, so we can start with some few exercises just to refresh memory about the conditional expectation. So, okay, the first exercise is, okay, I should have started like that, in fact, before to start the lectures, but okay, is the conditional expectation of a random variable something clear for everybody? So if it is clear, you should be able to give me the definition of the conditional expectation. So
yeah, okay, I can give you one.
Yes.
So it is an expectation of like the conditional, the expectation of A under the condition B is the expectation of A and B divided by expectation of B.
Okay, that what you say is not exactly the conditional expectation. It is the probability, probability than B given A.
Yeah. Oh, sorry.
No, don't be sorry. So it's okay. Yeah. I agree with the definition that you gave, but it is for the conditional probability. Now, what I want to, okay, it is not a very clear this question. Maybe it is a conditional expectation of a random variable.
Yeah. Okay.
Respect to some sigma field. So I have some random variable X and some sigma field G, and I want to know what is the definition. So it is, you have X, which is in L1 of some probability space omega with some sigma field F and P. G is some sub sigma field of F algebra. And the question is, what is this object? When I write this guy, what it is? What is the conditional expectation of X given G? I think that you should know what it is.
I just don't remember what it is.
Okay, somebody remember on, because that will be very important in the course. Conditional expectation is really fundamental. Okay, so I recall you what it is. Somebody want to say something? Okay. Okay, first, it is a random variable. And in fact, is the unique random variable which is G measurable. So it depends only on the events of G, of the sigma field G, such that for every G measurable random variable capital G, the expectation of Gx is equal to the expectation of Gz.
Well, I think I remember what is the thing. So yeah, it depends on the, like, it's easier to say what is if we have X and the condition is just the this beautiful letter is G, yes, G equal to Y. So just G small, some G small, and then we can like say that it is something. If we would have finite
finite values.
Finite values, yeah, it would be like expectation of X when like G is equal to G small divided over the measure of
G small, yes.
Of G small, yes. And here we should have something like derivative.
Yes, I agree. So that is for when you have some random variable, which are discrete random variables. But there is the more general theory here is when, for example, if X is some random variable which has a density with respect to the Lebesgue measure, and G is generated by random variables which are continuous random variable, not discrete random variable. So in this case, you cannot write some explicit formula more or less as you proposed to me in the case of discrete case. So it is some existence theorem. So of course, existence theorem is a bit always theoretical. Existence theorem is not so useful in practice because then you want to compute things. So we'll see in the exercise, but you have to know this definition. Definition is the unique random variable, which is G measurable. Of course, it is very important to be G measurable because otherwise I could take here in the definition, I could take Z equal to X, and then this equality would be trivially, this equality here is trivially satisfied if I say Z equal to X. But the problem is that X usually is not G measurable. It is just F measurable. And so you say that if you concentrate on the action of the random variable on the function g of the random variable capital G, which are G measurable, then you don't see the difference between Z and X. And so this is the definition of conditional expectation. And then there are many properties of the conditional expectation. So maybe I have to list them just to refresh the memory. So first, the conditional expectation is linearity, which is very important. Okay, so it means that the conditional expectation of alpha x plus y given g is alpha, or alpha is a number, the scalar deterministic number, x and y to random variable. The conditional expectation alpha x plus y given g is equal to alpha exponential of conditional expectation of x given g plus conditional expectation of y given g. So it is a linearity. There is also this property, which is that the expectation of that I used previously in the course is equal to expectation of x. So you don't modify this conditional expectation. The conditional expectation is some new random variable, but in average, it is the same as the initial random variable x. You have also this property, which is the fact that if x is independent of g, then the conditional expectation of x given g is just the usual expectation, which is a constant. Then it becomes deterministic. It is no longer random. It is deterministic. You have also the fact that if x is a g measurable, which is this one now is triviality. In fact, the conditional expectation of x given g is just x. And that comes from the definition, because the conditional expectation is a unique g measurable random variable, and x is, which satisfies the condition that I mentioned before, which is trivially satisfied by x. So it's the reason for which this property here is trivial. In fact, this one you can also see directly from the definition, because of course this constant exponential of x is a g measurable, because it is just a constant. And if x is independent of g, when you come back to the definition here, some time to refresh, I don't know why it disappeared. You see, if x is independent of the sigma field G, calligraphic G, and then the expectation of x times G, just expectation of x times the expectation of G. And so you can choose for Z expectation of x. It will work. It will make the job. So it's the reason for which the second condition that I wrote is correct. And the last one is very important. So it is a tower property of the conditional expectation. Which is that if you take H, calligraphic H, included calligraphic G, okay, which are all included in F, sigma fields. Okay, so you have some sigma fields which are ordered in this sense for the inclusion. If you have some event in H, then it is some event of G. Then you have the conditional expectation of x given G. This one here is a random variable which is G measurable. But G measurable doesn't mean that it is H measurable. So you can ask, what is the conditional expectation of this random variable with the smallest sigma field, H? And then that is the conditional expectation of x given H. So it is a tower property. If you take the conditional expectation respect step by step by taking first the conditional expectation with respect to the sigma field G, and afterwards you take respect to the sigma field H, it is the same as if you take directly the conditional expectation with the smallest sigma field, which is H. These are the basic properties of the conditional expectation, which permits to make a lot of computations. And okay, in the exercises, we will see also some other second important formula and to compute in practice sometimes conditional expectation. Several times in applications, the sigma field G here is given by the sigma field generated by some random variables. But it is not always the case. So it is good to remember this formal definition, theoretical definition of the conditional expectation. So let me come back to the exercise. Okay, yes, one. Okay, let me tell you something else before to make the second exercise. There is some other interpretation that for me, it's the best interpretation of the conditional expectation. What is conditional expectation? So if you take X in L2, okay, second order moment of X is finite, then expectation of X given G is the unique random variable G measurable such that the expectation of X minus Z square is minimal. You see if it's okay here, what you see is mainly the L2 norm. So it is some distance between X and Z. And you ask, what is the best approximation that I can have of X by using only G measurable functions, G measurable random variable. And the best approximation is given by this random variable, conditional expectation of X given G. This is the one which minimizes this L2 distance between X and Z. Okay, so it is a so it means that you have only the information. So if you think in a different way, when you have a sigma field G, it means that you have some information which is restricted with respect to information that you could have if you knew all the events which are in the big sigma field. So you have less information, and you are saying with this information which is encapsulated in this sigma field, I can construct many random variables. Okay, just for example, indicator function of some A, where A is included in G. It is a random variable which is G measurable. And I can take some linear combination of these indicator functions. So I can construct with this information that I have about the events in G, I can construct some random variables, and I try to minimize the distance between the real X, which is not G measurable, and some random variable which is G measurable in the L2 sense. The L2 sense in the sense of the quadratic norm between X and Z. And the one which minimizes this distance is the conditional expectation. So, but this interpretation works well if X is in L2, if X is in L1, so this guy a priori doesn't make sense, so you cannot use this interpretation. But it is a way to interpret it. So we will say that, in fact, let us come back to the second exercise, which is, now it is a bit different. We take, we take X, which is some random variable which take only two values, 0 and 1. So it is some binary random variable. Okay, and so we have Y, some other random variable, but with values in R. so which is not a priori in values in 0 and 1. And so I'm asking, what is the best function phi, which send with values in the set 0, 1. So we take only two values, 0 and 1, set that the quadratic distance between x and phi of y is minimal. So it looks like a bit like what I said before. If I didn't, because the conditional expectation of x, x given y, is just one which minimizes the distance between x and y.
Does anybody can hear something?
Now, yes. No.
Okay, so nobody hears Cedric, I guess, yeah?
Yes, I wrote him, but he doesn't see it, obviously.
Do you hear me now?
Yes, now we
Okay,
can.
sorry, it was there was some problem. Disconnected. Okay. And okay. Do you see my screen now?
Yes.
Okay, so I don't know when it was stopping. I was looking for nothing. So, okay, we are in this exercise 2. We have to determine this best measurable function that such that the expectation between x and phi of y in L to norm is minimum. Okay, the difference with the usual conditional expectation is that it would be the same if I didn't ask of phi to be with values in 0, 1, but with values in R. Now I had some constraint. There's only to take 2 values, 0 or 1. And okay, so it doesn't remain so much time. Maybe, I don't know if somebody has some ideas or how to attack this problem. No ideas. Okay, so what we will do. So we want to minimize phi is a function which goes from R into 0, 1. So it takes only 2 values. And we want to minimize this expectation of x minus phi of y squared. So what we do is that we can write it like, so x and y are two random variables. Maybe they are independent, maybe they are not independent. Okay, so let's have some common law, joint law. So I denote by pxy the law of the couple xy. And we remember that x takes only values in 0, 1. So in fact, this guy, I can write it like according, I can split the space into spaces, the space where x is equal to 1 and the complementary space where x is equal to 0, because x can take only these 2 values. So it is the integral over omega that the probability that x is equal to 1 and okay, y is in R. So maybe I use what is called the transfer formula. So it is y is equal to y, okay. So times 1 minus phi of y squared. Okay, plus the integral over R dp x equals 0, y is equal to y, and the correct function minus 0, sorry. Now x is equal to 0, so I have only phi of y squared. You agree with that? And now what I do is the following. I will use conditional probability that Alex was mentioning before. So I will say that this first probability is the same as the probability that is dpy equal y times the probability of x equal to 1 given y is equal to y. 1 minus phi of y squared. This is just base formula. okay, plus, okay, I could do the same for the other guy, but I have to remember that, in fact, dp x equals 0, y is equal to y is equal to 1 minus dp x equal to 1, y is equal to y. Okay, because x can only take two values, or 0 or 1. So here I split his second term, which is here, according to his equality here. So the first guy, oh, sorry, I should write, it's not totally correct, but I wrote, it is not that, because it is dp y is equal to y minus dp x equal to 1, y is equal to 1, because I have also I have the intersection with the event y is equal to y. So it is integral over r dpy is equal to y phi y square plus minus dp x equal to 1, y is equal to y, phi y square. Okay, so I just rewrote this guy, which was written here. I rewrote it as the following difference. And again, here, I will use base formula to replace this guy by this guy. Okay, if I do that, then I will have this guy is in fact equal to this guy, and I can put together this guy with this guy. Okay, and then what I will get is the following. I will get that it is the integral of r integrated with respect to the law of y of probability that x equal to 1 given y is equal to y times 1 minus phi y square plus phi y square there is a minus, sorry. Plus integral of r phi of y squared dpy is equal to y. Okay, just what I did to get this formula is just to replace this guy. I replace it by this guy. And then once you replace this guy by this guy, you see that you can regroup this guy with this guy. And it provides me this term, which is here. And the other one, which was here, just here, with the plus. So now, if I continue like that, what I can rewrite it like the integral over r dp y is equal to y. So this is fixed. Okay, it is fixed by because the y is fixed, x is fixed. So I cannot choose it. The unknown is the phi, which is minimizing this expression. So the unknown is phi. And then I can write it like, so if I regroup together the different terms, I get phi y square times 1 minus x equal to 1, y is equal to y, plus 1 minus phi y square, right, that x equal to 1, y is equal to y. But we have to remember that phi is a function which goes from r into 0, 1. So it can take only two values. or the values for which phi is equal to 0, and the values for which phi is equal to 1. So in
sorry,
fact,
didn't we lose minus phi of y squared? Maybe it should be with minus. Sorry. Maybe not.
No,
Yes,
because you see here it is a plus. Here it is a plus, it is this term. And this term, I agree that there is a minus here, but this minus is here. So I would not say that I lose something.
Okay, sorry.
So so now I have to find the function phi which minimize this expression. And phi can only take values 0 and 1. So so I have to decide when phi of y is to be equal to 0, when phi of y is equal to 1. So as you can see, if phi of y is equal to 0, then this expression which is here is equal, okay, let me call it a of y. A of y is equal, if phi y is equal to 0, it's equal to probability that x equal to 1, y is equal to y. Okay, which is positive. If phi of y is equal to 1, then a of y is equal to, it is 1 minus the probability that x equal 1 given y is equal to y. Okay, so now it is phi that I can decide. So in fact, if I want to minimize this expression, I have to define phi in order that between these two expressions, it is always the one which is the smallest possible. So it means that, for example, if his quantity, if his quantity, for example, if imagine that this quantity is 1/3, if it is 1/3, here you have 1/3, but here you have 2/3. So what is the smallest? Because there's the smallest between 1/3 and 2/3, it is of course 1/3. So if this quantity is 1/3, I have to say, phi y is equal to 0. But for example, if this quantity is 2/3, then it is 2/3 and it is 1/3. So if I want to take the minimal value, I would prefer to say, okay, take phi of y equal to 1. So in order to minimize, what you have to do, so to minimize this expression, you have to take phi of y is equal to 1 if 1 minus probability that x equal 1 given y is equal to y is smaller than the probability that x equal to 1 given y is equal to y. Because otherwise, what I will do is that we'll take the opposite. Okay, and phi y is equal to 0 if 1 minus probability x equal to 1, y is equal to y is bigger or equal to probability that x equal to 1, y equal to y. And so it says the conclusion is that the phi, which is minimizing this expression, phi of y has to be equal to the indicator function because it is 1 or 0. And if you look at what is this inequality, so we can put this p here on the other side, and you see that at the end, what you get is that it is an indicator function that the probability that x equal to 1 given y equal to y is bigger than 1/2, which is of course a deterministic function of y. Okay, and so it is the function which minimizes the quantity of interest. So this is a solution. So the function minimizing expectation of x minus phi of y square among all the functional values in 0, 1, among all the phi's with values in the set 0, 1 is phi of y, indicator function of probability that x equal to 1, given that y is equal to y, is bigger than 1 half. Okay, so is the proof clear? I suspect that means yes.
Yes, I think it's clear.
Okay, so anyway, I will send you this, I will transform this computation in some PDF file, and I will send it to you by email with the slides of the lectures also. But for that, I need to have all the address email of everybody. And for the moment, I think that I have only a few ones. So the people will save my previous email. It means that I have their emails, but the other ones, I think there are more who didn't receive my previous email, means that I don't have their address. So please send me some email. I put my email in the chat in order that I can send you all this material. Okay. So, okay, it doesn't remain a lot of time. So I'm not sure that we'll have time to start some new exercise. Well, it doesn't make sense to start some exercise. I will not have time to finish the exercise. So I don't know. Do you have some questions? Or about the organization of the course, if there are some problems, if I assume too much from what your background, if I'm too little, if so.
Yeah,
no
for
question.
example, for me there were a lot of new things here, and some of them like were studied long ago. Yeah.
So can you precise a bit what was new? For example, the conditional expectation, I thought that was not so new, in fact.
Yeah. Well, it wasn't so new, but for example, the word stochastic was met by me for the first time, I think.
As stochastic, you mean stochastic processes and so on?
Yeah.
Okay, yeah, so that I can agree. But okay, stochastic process is just a collection of random variables which are indexed by n. So
okay.
When you have seen the stochastic processes that you have seen in the past is when you take a sequence of IID random variables. It is a special case of stochastic process where you assume that all the random variables are independent and identically distributed. But when you take, for example, a Markov chain, then it is not composed of random variables, but it is a stochastic process. Because at each time n, you have some random variable xn, but there is some dependence between the random variables. But I can assume that Markov chains, you have seen Markov chains.
Yeah, I've seen.
But probably just in the countable or finite state space, not in some general space like R. Markov chain.
So it was like, it's
okay. Discrete, okay. So, okay, the theory is not so different if it is discrete or if it is not discrete, if it is a general measurable space. Just the difference is that in this case, you can introduce these matrix transitions, and now you have to work with these kernel transition probabilities that I define, this QN. But this QN are some kind of generalization of some matrices, but which are indexed by the continuous space. So,
yeah, thank you for the explanation.
okay. So I don't know if somebody has some other comments or some questions.
Yeah, and so Paulina, are you here? Paulina asked to have a time later, but I, on the contrary, have like a restriction from above. On the second, on the like Saturday session. Yeah, so I would prefer that it will be earlier. Yes.
Wait, so let me come back because now I don't remember exactly. So it was here.
Yeah, we stated it for 3:30. Yeah.
Yes. So that is not good for you, or?
Well, for me, like the ideal time will be like 1 hour 00. Yeah, or something like this. And I wonder maybe Paulina also is okay with this.
Yeah, but I didn't understand. Is it okay this one, or it is you prefer that it start before? Or?
Yeah. I prefer it starts 2 hours 30 minutes before.
At 2 p.m. you mean, or 2 hours before?
At 1 p.m. Yeah.
Okay, and the other people is so I can.
Yeah, but I wonder if Paulina is here because.
And Paulina, what do you want?
Yeah, because this 3:30 was proposed by Paulina. That's why I'm thinking about her.
Paulina, you are here, or maybe she's not here, no? She's not.
Oh, I see. The problem is that in Chicago it's early at the morning, so she wants later. Yeah, okay. I see. Probably she won't be okay with earlier time. Yeah.
Okay. Well, I don't know. Could you confirm me by saying maybe you have to discuss with her. But,
yeah.
Could you confirm by email? But if 1 is okay, or otherwise I will start with his 1 p.m.
Well, I'm pretty sure she's not really happy with it because I just watched the time in Chicago and it's like now it's 43 minutes past 9 a.m. and so yeah, it's early even now.
And for you, 3:30 is not okay.
Yeah, because I have like at the evening I have I have some things to do.
Okay, so I don't know what for the other people it's 1 or 3:30 is irrelevant. We can share. We can start at 2. So it will be okay. It will not be optimal for you. It will not be optimal for Paulina, but we can maybe.
Well, for me, the ideal ending time is 5 or earlier. So for me, 2 is absolutely, not, but 2 is okay. Yeah, 2 is okay.
2. So we can start with 2. 2
yeah.
will finish at.
And and I suppose I will record. By the way, I think I should stop recording because this discussion. Well, I won't stop till we will have some resolution about time. Okay, so yep.
So okay, for the moment I assume that it is this time that we decided.
But it's I suppose it's 5:00 or from
yes, I know you're right. You're right. Yes, 5:00. Yes, not so much. 5:00. Yes, 2 to 5.
Yeah, so it's okay with me.
Okay, good. Some other question apart from Alex or?
So thank you, Cedric, for the lecture.
Okay.
See you next time.
Okay, thanks. Okay, if there are no other questions, we will stop and we will meet us next Friday. And I will send you some slides and also some beginning of the exercises and these things that I wrote today on the iPad. Okay.
Yeah, thank you.
Okay. So bye to everybody. See you next week. Bye.
Thank you. Bye.
Bye.
Thank you. Bye.